Welcome back. In this video, we're going to look at the role of subspaces in machine learning. So objectives are to first define what we mean by a subspace, establish the centrality of those in the kinds of machine learning problems we've been looking at. We'll introduce the dimension of a subspace and what that implies for low-rank approximations of matrices. So subspaces play a key role in many machine learning problems. So far, we've looked at the classification and data modeling problem, which leads to solving the system of equations AW equals D. Well, if we look at the types of solutions that we can obtain using this, AW is just a weighted combination of the columns of A. So this solution has to lie in the span of these vectors. It has to be able to be expressed as a weighted sum of those vectors. Similarly, we introduced the idea of modeling matrix data, such as ratings of users, as an outer product of a matrix T times a matrix S, R hat denoting our approximation or our model. And if we expand this out, we had written it previously as the sum, I equals 1 to m, of T sub I, S sub I. But if I look at this in terms of the columns of R hat, we see that each column can be written as a weighted sum of the columns of the T matrix. So in this case, each column of R hat lies in the span of this set of vectors in the matrix T. So in both these important problems, we have that our approximations or our solutions lie in the span of a certain set of vectors. The span of a set of vectors, say v1, v2 through vm, is a subspace. We'll formally define a subspace in terms of mathematical terminology as a set of n-dimensional points S, so they lie in the space Rn, and they satisfy the following three properties. First of all, the zero vector is in this set. In other words, the origin is included in the subspace. Secondly, if a vector f and a vector g that are in the subspace, then the sum of f and g is also in the subspace. And this means that you can add any pair of terms in the subspace and stay in the subspace, so it's closed under addition. And then third, if a vector f is in the subspace, then we can scale that vector, in other words, multiply it by a scalar alpha, and that scaled vector is also going to be in the subspace. I can shrink the length of a vector, or I can make it longer and it stays in the subspace. Let's take some examples. So let's first consider the set of points x, y, z in 3 dimensions where z is equal to 0. Okay, so this is the xy plane in 3 dimensions. Well, first of all, the xy plane includes the origin 0, 0, 0, so that property is satisfied. And then if I look at some point f in the xy plane, say it has coordinates fx, fy, and then the z component is 0, I have another point G with components gx, gy, and the z component being 0. If I add those two, I get yet another point in the xy plane, fx plus gx, fy plus gy, and 0. So that second property is satisfied. And then if I take some point in the xy plane, say with coordinates fx and fy, and I scale it or multiply by the scalar alpha, this just changes the length of the individual coordinates, so that also is in the xy plane, and therefore the xy plane is a subspace. Now suppose we define a set S where the points are, again, triples x, y, z, so it's 3-dimensional space, but this time suppose we consider it to be the plane where z is equal to 1. We can see right away that since z is 1, the point 0, 0, 0 is not an element in this set S, so this cannot be a subspace. I'll take one more example here of in 3-dimensional space. Suppose we define the set of points S as the triples x, 2x, x. And if you graph this, when x is 0, we have 0, 0, 0, so 0 is in that space. When x is 1, we go through the point 1, 2, 1. Similarly, when x is minus 1, we go through the point minus 1, minus 2, minus 1. And this becomes a line running through 3-dimensional space. Well, you can check that if I have some point F on that line and another point G on that line, then the sum of those 2 points is also on the line. This line in 3D is closed under addition. Furthermore, if I have some point on the line, say F, that has coordinates F, 2F, and F, and I scale it by alpha, that gives me yet another point on that line. So this line in 3D is a subspace. We motivated looking at subspaces from the classification and modeling problem and then the matrix approximation problem. And in those cases, we saw that we had a span of a set of vectors. And so let's suppose we define a subspace to be a weighted sum of vectors v1, v2 through vm. And I can write that compactly as a matrix V times a vector W, and we'll assume that we obtain this set of points by letting W take on any set of values in m-dimensional space. So V is an n by m matrix. In other words, this space is within Rn, and we have these m degrees of freedom that are associated with the vector W. Well, again, we can check through our 3 properties. We see that when W is equal to 0, VW is equal to 0, so the origin is in this particular space. If I take some point in the space F, which is expressed as V times WF, and another point G expressed as V times W sub G, and I add those 2 vectors, F and G, well, I can factor out the V, and I end up with V times another vector, WF plus WG, and that is also in the subspace. And then finally, if I have some point F, which is expressed as V times W sub F, and I scale F by a scalar alpha, the scalar commutes with the matrix V, and I can rewrite this as the matrix V times some new vector, which is alpha times WF. And again, that is in this space, so we've shown that the span of a set of vectors V is a subspace. Now we say that the dimension of this subspace is the rank of the matrix V. We can look at some examples. If I define V to be 1, 2, 0, V times W will give me then a line in the xy plane with slope 2 that goes to the origin. This matrix V is rank 1 because it has a single vector, and a line is a one-dimensional quantity, and this particular line lives in 3-dimensional space. Now let's take another case where V has a green vector 1, 1, 0, a pink vector 0, 1, 0, and then a blue vector 1, 0, 0. If you look at this matrix, you can tell by inspection that the rank of this matrix is 2, and if I graph these 3 vectors, I see that any weighted combination of these vectors is going to lie in the xy plane. My rank is 2, and I've seen that the dimension of my space is 2. There are 2 independent components associated with the coordinates in x and y, and z is defined to be 0. In general, if we look at this as a set V times W, where W can take on any value, this will lie in a k-dimensional hyperplane containing the origin in Rn. If k is 1, then we're representing a line through Rn. If k is equal to 2, then we've got a conventional plane through the origin in Rn. And you can think about this in k equals 3, 4, and so on, although it's difficult to visualize, and we call these hyperplanes in these higher dimensions. Now, an important problem that we want to address in this context is this matrix approximation, where I have an approximation that I'm forming R hat to some data matrix, perhaps ratings of users, as a product of a matrix T and a matrix S. And we might want to ask, what is the dimension of this space, or what does this space look like? Well, it turns out you can show that in general, the rank of a product of matrices is bounded by the minimum of the rank of the individual matrices. So it can't exceed the rank of T or the rank of S. In the special case, when T is an n by m matrix, and the rank of T is equal to M, and S is an M by K matrix, where the rank of S is equal to M, you can show that under these conditions, the rank of this approximation, R hat, is equal to M, or if rank of R hat is equal to M, then these two matrices have to also be equal to M. And I've got proofs of both of these in the notes associated with this lecture. So if we take some ratings matrix R or some other data matrix and we represent it as a matrix R hat, where we write R hat in this outer product form, recall we talked about the columns of T being tastes, and then rows of the matrix S are weights that tell how those tastes are put together. If there's M tastes, or T is an N by M matrix, then we call this a rank M approximation to the matrix R. So it's a low rank approximation because in general, M is going to be less than N or K, the dimensions of R, and we're representing this N by K matrix with M linearly independent terms. And this implies that the columns of this matrix R hat, our approximation, that they lie in an M-dimensional subspace. So again, we can illustrate this in 3 dimensions. Suppose we take the case where T has a column 1, 1, 0, and then 0, 1, 0, and then S has a row 1, 1, minus 1, and a second row 0, 1, 1. Well, you can check that both of these matrices are rank 2, both T and S, and if I do the product, my matrix R hat is 1, 1, 0, shown that in orange, 1, 2, 0, which is in pink, and negative 1, 0, 0, which is in green. So I've graphed these 3 vectors representing the 3 columns of R hat, and you see that they are confined to the XY plane because the Z component is always 0. These 3 vectors lie in a 2-dimensional space. So if this is a rank 2 approximation to some matrix R, that might be a very good approximation in the case where the 3rd component of R, in other words, the Z component of the matrix R, is generally very small relative to the X and Y components. Then we can approximate the dominant part of R as lying in the XY plane. Now, more generally in 3 space, we could have a rank 2 approximation that lies in some other plane going through the origin. It's just a little bit more difficult for me to draw that.